Yeah, so now we'll be dealing with operating systems. In the subject operating systems, deadlock is a very important topic. So, in this topic, what are the things we are going to look? So, we'll be looking at the description of deadlocks, and then because of deadlocks, the concurrent process cannot happen together. And then we also deal with several methods for preventing and avoiding deadlocks in a computer system. So, this entire course on deadlocks is based on from a textbook by Skillbox Schwartz and also Berkeley Operating Systems Group. Now, getting on to this, in this topic deadlock, we'll be dealing with subtopics, the system model, deadlock, what are the characteristics of deadlock, and how are we going to deal with deadlocks. We also deal with how to prevent deadlock, how to avoid deadlock, and how to detect a deadlock, and once a deadlock has been detected, how to recover from it. Now, we have a law called as Consensus law. So, according to this, when two trains approach each other at a crossing, both shall become to a full stop and neither shall start up again until the other has gone. So, what does it mean? You have only one train track, but then from both the ends of the track, there is each train coming towards each other. So, ultimately, none of the train can progress forward unless and until one train completes its give up. So, deadlock is such a kind of situation where none of the train is ready to go back, but they want to progress further. Ultimately, none of them progress. So, this is the same as the story of the two goats, where you have only one bridge, where two goats fight with each other to pass the bridge. They don't have patience to wait. If one wait, then the other can go, and later, after a certain time, the other one can cross. That's what it is. So, how does we model a system? So, a system consists of several resources. Like, say for example, you have several resource types. You have CPUs, you have memory spaces, you have input-output devices, etc. So, similarly, and you call it different cycles. Say for example, you call these different types. Input-output devices are different types, and your memory units are different types. So, each resource type have different instances. Say for example, you might have 4 printers, you might have 2 keyboards, you might have only 4 memory units. All these things will have different instances. So each process utilizes a resource as following. Say for example, if I need to use a resource, first I need to have the resource. So in order to have the resource, I need to request the resource. Once I request the resource, then I can use it. After use, I cannot hold it. After use, I'll have to release it no matter what, so that the other person or the other process can use it. So there are three ways, that is request, use and release. Next one is, how can you tell that this deadlock can occur? Say for example, there are 4 conditions which should hold true for a deadlock to happen. The 4 conditions are namely mutual exclusion, hold and wait, no preemption and circular wait. So, in mutual exclusion, what it actually tells is, if I have a resource, if I am using it, none of the other ones should be using it. That is, if I have a printer and one process P1 is using it, then the remaining process P1, P2, P3, P4 have to wait till the process P1 finish utilizing the printer. Next condition is hold and wait. So the hold and wait is nothing but a process holding at least one resource is waiting to acquire additional resources held by other process. That is, if I need a process, okay, I should only wait. Okay, say for example, I am not willing to give any of the process. Okay, if I am not willing to give any of the process, say for example, I have 3 printers, and then process P2 has 2 printers, but I want 4 printers and process P2 requires 3 printers, but then we have 3 printers and then P2 has 2 printers respectively. However, none of the processes are willing to lend one of the printer. So this is a hold and wait scenario where I ultimately hold something and I don't give the 3 printers, but I always wait for the 1 printer. No preemption. That is, this is a very important property. What do we mean by no preemption is that See, you cannot force me to give the resource. That is, I'll hold the resource unless and until I want it, or I'll only release the resource only if I wish to. So a resource can be released only voluntarily by the process holding it after the process has completed its task. That is, you cannot force me telling that give the process I want it. Next, circular wait. So circular wait is also a similar kind of, say for example, it is also like your hold and wait, where in circular wait you will having n number of process, say from P0 to Pn you will have n number of process. Each process, say that P0 is waiting for a resource that is held by P1, there will be a cycle. P1 is waiting for a resource that is held by P2. Similarly, Pn minus 1 is waiting for a resource that is held by Pn. And Pn is waiting for a resource that is held by Pn. So similarly, everyone is holding a resource and then they are waiting for other resource. So this is also leads to deadlock. That is, ultimately it is not leading to progress. So it is not that the three, ultimately all the four conditions, say namely the mutual exclusion, hold and wait, no preemption and circular wait, if all these happen together, then you can tell deadlock has happened. So this is how you have to draw a resource allocation graph. For a resource allocation graph, you will have two types of nodes. That is, V, you have a set of nodes V, and then these nodes are partitioned. You will have two kinds of nodes. One is the process nodes and the other one is called as the resource nodes. And then edges. Again for edges, you will have two edges. One is the requested and the other was the edge, assignment edge. So the request edge is from this process is requesting for this particular resource. So if it is from P to R, it is a request edge, and if it is from R to P, it is an assignment edge. That is, this particular resource is assigned to this process. Now you have process. A process is represented by a circle node, and then a resource is represented by a square node. A square within a square, the squares within the square denotes the number of instances that are present. So this is an example of a resource allocation graph where you will have P1, P2, P3 are three processes and they are represented by circular nodes, and R1, R3, R2 are resources, R1, R3, R2, and then R4 is also a resource. The three dots inside R4 denotes there are three instances or three numbers of R4 resources. Similarly, for R1 there is only one instance, R3 there is only one instance, and R2 there is two instances. So at this point we will have to check, we will have to draw the assignment edge, and then we will have to traverse to the graph and check whether there is a cycle or not. If there is a cycle, then we can tell that the processes are deadlocked. Say for example here, P1 is being requested, P1 is requesting R1, R1 is been held by P2, and P2 is requesting R3, and R3 is being held by P3, and P3 is requesting R2, which is ultimately held by P1. So there is a cycle. Fine. If there is a cycle, then you can tell that there is a deadlock. Fine. Thanks a lot.